Alright, welcome back everyone to another AMC problem solving strategy video. My name is Sol, and today we're going to be going over a number theory problem from the AMC. Now, before we get into the problem, this problem kind of incorporates concepts from, or the three concepts that I went over last video. So if Chinese remainder theorem, Fermat's little theorem, and Euler's theorem don't really ring a bell, I highly recommend you go check out the video that I previously posted. Otherwise, you guys can stay and watch me walk through this problem, kind of show my thought process if this showed up on the AMC. So this problem is problem 11, as it says, and I think it's from the 2011 AMC 1. So let's get into it. It says that R is the set of all possible remainders when a power of 2, when the power is not a negative integer, is divided by 1,000. Okay, and it says that S is the sum of the elements in R, and it wants to know the remainder when S is divided by 1,000. Okay, so this is a pretty concise problem. There are definitely wordier AMC problems out there. And we might not know where to start, because the powers of 2 kind of have this cyclic nature when divided by 1,000. And, well, how are we supposed to come up with that? Well, I mean, the powers of 2, let's say mod 10, a much smaller power of 10. Well, this can be anything from 2, 4, 6, or 8, right? And since these powers of 2 mod 10 have a cyclic nature, maybe we think that the powers of 2 mod 1,000 also exhibit a similar behavior. So that's kind of our motivation, our inspiration for this problem. So the objective is to essentially find some 2 to the n that is congruent to a 2 to the n mod 1,000. Right? Such that we'll just say that n is less than m. Alright, cool. So, well, you guys might be thinking, well, why isn't m just n plus 400? And where did I get 400 from? Well, that's just from Euler's theorem, right? Phi of 1,000 is equal to phi of 8 times phi of 125, which makes it equal to 4 times 100, if I can write it, which is, of course, 400. So we kind of get the idea that these powers of 2, or anything mod 1,000, powers of anything mod 1,000 move in cycles of 400. So maybe we think that there are 400 distinct remainders, 400 elements in R. Well, the problem is this isn't true, and the reasons get kind of complicated, but one of the main reasons behind it is because 2 is not relatively prime to 1,000, and so the cycle, or the amount of elements, the number of distinct remainders, is actually a divisor of 400 instead of just 400 itself. But that's kind of confusing. Let's just try to deal with this expression that we have in front of us. So, the first thing that I would do is I would subtract 2 to the n from both sides. Now, you guys might be thinking, okay, how am I supposed to think of this on the exam? Well, first of all, maybe you just want to try something, right? Just subtract 2 to the n from both sides. But my main motivation for this step is just that, well, I would much rather deal with a multiple of 1,000 like we have here than, say, a multiple of 1,000 plus a power of 2 like we have in this first step. And then the next move that I would do, or the next thing that I would do, is factor a 2 to the n from this thing. So this would be 2 to the m minus n minus 1, which is congruent to 0 mod 1,000. And we can do this because we've assumed that n is less than m, so that means m minus n is going to be a n minus n is going to be a positive integer, a non-negative one at least. Alright, so looking at this, what is the next step? Well, we have that this thing on the left side is a multiple of 1,000. And one thing I notice is that this is odd. Now, why is that? This is going to be odd if, well, 2 to the m minus n is even. The only time that 2 to the m minus n is odd is if m is equal to n, but we've assumed that m is strictly greater than n, which means that this factor right here is necessarily odd. Why is that important? Well, that's important because now we know that this right here is, well, even, and we know that 1,000, any multiple of 1,000, has a minimum even factor of 8. Now, why did I bring up the minimum? Well, we want to find the minimum values of n and m because we don't want to overcount these possible remainders, these elements of R. If we overcounted, then we would get an incorrect value of s, which means that our answer would be wrong. So since we want to find a minimum value of n and m, the minimum value of n would assumably be 3, because every multiple of 8 is divisible, or every multiple of 1,000 is divisible by at least 8. So we can say that n is equal to 3, and that means we have that 2 to the third is times 2 to the m minus n minus 1 is congruent to 0 mod 1,000. Cool. The next step that I would take is to notice that since we have our minimum even factor right here, actually I can replace this n right here with a 3. The next step that I would take is to notice that since this is already 8, we need at least a factor of 125 from this odd factor that we found, or from this factor that we found to be odd, rather. And yeah, so we kind of get the idea that 2 to the m minus 3 minus 1 is a multiple of 125, right? And this should make sense because if this is like some 125k times 1,000 times 8, it's going to be some 1,000k, which makes it a multiple of 1,000. So we can rewrite this expression as 2 to the m minus 3 is congruent to 1 mod 125. Alright, so let me just clear up the board and then we will continue the problem from there. Alright, so just to pick up where we left off, we found that this n is equal to 3, this smaller value of, this smaller power of 2 is equal to 3, and we found that 2 to the m minus 3 is congruent to 1 mod 125. Well, I hope this 2 to the something is congruent to 1 mod 125 looks very familiar, especially if you watched last video, and that is because we know that 2 to the phi of 125 is congruent to 1 mod 125. Now, we can say that phi of 125 is equal to m minus 3, and phi of 125 is 100, which means 100 is equal to m minus 3, and therefore m is equal to 103. Okay, so before we finish up the problem, we need to, I want to discuss something, and that's mainly this equation that involves phi of 125 and m minus 3. Why can we simply just set the exponent equal to phi of 125? Why couldn't we do that before? Well, like I said while explaining that part, 2 is not relatively prime to 1,000, meaning that the cycle of the amount of distinct remainders of powers of 2 mod 1,000 is not 400, it's a factor of 400. And well, 2 is relatively prime to 125, meaning that the powers of 2 have a the powers of 2 mod 125 have exactly 100 values, and that's why we can say, and that's why this kind of thing, or this equation works. It makes sense. So we found that 2 to the third is congruent to 2 to the 103. So assumably, we can say from here that the distinct elements of R are the remainders when 2 to the 0, 2 to the first, 2 to the second, so on and so forth, all the way up until 2 to the 102. These are all this, and let me just stick a mod 1000 here. These are going to be all of the distinct elements of R. If we put in 2 to the 103, 2 to the 103 is the same thing as 2 to the third, as we've shown, which means that we'd be overcounting this remainder, right? So let me go ahead and clear up the board, and we'll finish off this problem. Alright, so just now, we have found that the remainders in R are all of these elements, all of these powers of 2 mod 1000. And it says it wants us to find the sum of all of these elements. So, well, that's pretty easy. We can take a geometric sum and then mod 1000 and then just divide it by 1000. And we can do it again to find the remainder when s is divided by 1000. So, let's see here. Well, the formula for a geometric sum, or for a finite one at least, goes like this, right? Where R is the common ratio between each term, A is the first term, and N is the number of terms. So, well, the first term is 1. The ratio is 2. There are 103 terms, careful for this, because it's 102 minus 0 plus 1. And then it's over 1 minus 2. And this is the same thing. I'm just going to flip negative signs as 2 to the 103 minus 1 over 2 minus 1, which is just 2 to the 103 minus 1. Alright, and now it is our goal to try to find 2 to the 103 minus 1 mod 1000. Okay, so, well, we don't really know what this is equal to, and it's kind of intimidating to try and attack it with just, mod 1000. Well, I have an idea. Let's try to use Chinese remainder theorem. We don't know what this is, mod 1000, but we can certainly find what it is mod 8 and mod 125. I think that would be really, it would be definitely a lot easier than just approaching it from mod 1000. So, can I scroll down a bit? Not that much. Okay. So, let's find 2 to the 103 minus 1 mod 8 first. Well, it's easy to see that this first term is divisible by 8. So, this thing is just going to be congruent, congruent to negative 1, which is congruent to 7 mod 8. Perfect. And now we want to find 2 to the 103 minus 1 mod 125. So, mod 125, right? That's what we're trying to find. So, well, I know that 2 to the 100 is congruent to 1 mod 125 because 125 is 100. So that means that this is the same thing as 8 minus 1 mod 125, which is the same thing as 7 mod 125. And from here, we might be just tempted to say that, oh, this thing is 7 mod 1000, right? And that's just because, well, this thing is 7 mod 8 and 7 mod 125, so it's probably just 7 mod 1000. But just for the sake of proving it, just so that I can actually show you guys how to solve a system of congruences like this. Let me just drag this down here, create a little extra space, bam. Okay, so we know that, let's just call this A. I think that'll be easier, so let's call this A. So we know that A is congruent to 7 mod 8, and we know A is congruent to 7 mod 125 as well. So I'm going to mess with the second congruence first. We're going to say that A is equal to 125k plus 7, such that k is an integer, right? Is an element of the integers. Then I'm going to take this expression mod 8, right? So A is congruent to 7, as we know, mod 8 from this expression, and we wish to well, take this mod 8. So this is going to be congruent to well, 125. What is that? 125 mod 8. Well, I think that is 5 mod 8, because 8 times 15 is going to be 8 times 15 is 120, and what's left is 5, so that means this is probably 5 mod 8 plus 7, so we have something like this. So we decide to cancel both of these sides out. We get 5 is congruent to 0. 5k is congruent to 0 mod 8. And intuitively, this only happens when k is a multiple of 8, but to just illustrate how you're supposed to solve this, if, say, this was like a 1 or a 2, right? We want to find the modular inverse, and to find that, we just want to multiply this, we want to multiply both sides by some number, we'll call it x, right? Or actually I'll call it m. We want to multiply both sides by some number m, such that 5 times m is congruent to 1 mod 8. Because if we do that, then we're going to, then this coefficient in the front will simplify to 1, and that'll give us that k is congruent to something mod 8. So, well, 5 times m is congruent to 1 mod 8. Well, that's not too hard. We don't have to examine too many values since there aren't that many in the first place. I think the answer... Oh, wait. Well, okay, that works. 5 times 5. So m is 5. M is 5, because 5 times 5 is equal to 25, which is congruent to 1 mod 8. So we can multiply both of these sides by 5, like this, congruent to 5 times 0 mod 8, which gives us 25k is congruent to 0 mod 5, and from there we can say k is congruent to 0 mod, or wait, not 5, this is 8, 0 mod 8, and that's because 25, again, is congruent to 1 mod 8. Now, it is worth noting that this m will not exist if, well, if this 5, say, was a 6, if this coefficient in front of k was not relatively prime to 8, or the modulus. So from here we can say that k is going to be equal, or k is a multiple of 8, so we can say it's some 8b, I guess, I don't know, for some integer b. B is an element of the integers. And what have we found earlier? We found that a is equal to 125 times, we're substituting k in here, plus 7. A is congruent, or A is equal to 1000 B plus 7, and we want to find A mod 1000, right? So A mod 1000 is going to be 7 mod 1000. So since this is the AMI, we're going to finish off the problem. We're going to answer 007007, and we are done.